For a sample of gases, even if that's a mixture of gases, the gases have the same pressure and the same kinetic energy as long as they're at the same temperature. Now, the gases could be very different. You could have bromine, very massive, or hydrogen, very light, in the same container at the same temperature, but they'll both exert the same pressure on the walls with the same kinetic energy. Now, they do it differently. That is, bromine comes in with large, massive shots to the walls to exert pressure, where hydrogen comes in with lighter shots, but more rapidly. The property that differentiates the gases is their velocity. They have different velocities based on their masses. So the velocity is the distinguishing characteristic, and it would be nice if we could solve for that velocity. Our expression for the kinetic energy has the velocity squared, the mean velocity squared, in it. So we can solve for the mean velocity squared, take the square root, and we'll have a quantity called the root mean squared velocity. Now, it's not exactly the mean velocity, but it's very close, and it depends on fundamental properties like the temperature and the nature of the gas. So we can easily solve for that quantity. So let's do that. Here's the mean velocity squared in terms of expressions for the kinetic energy. So we have 3 Boltzmann's constant T over the mass of the particle, or for a mole of sample, 3 RT over the molar mass of the sample. Here we'll express R in joules, so our velocities come out in meters per second. We can take the square root of that quantity, and we'll get the root mean squared velocity, and that's our close to the mean velocity parameter that we want based on simply the temperature and the mass of the gas. So I'll take the square root of these 3 quantities, and I'll find a very simple expression for an important distinguishing property for the gases, their actual velocity. The root mean squared velocity for a mole of gas is 3RT over the molar mass, square root.